to tell us about challenging modeling assumptions by connecting optical and IR.
All right, so of course, first off, can everybody hear me? All in the back? Great. So I had actually also changed my title, but now I changed it back because I felt too many people were changing their title, and I had to do something. So my name is Kragh Jespersen. You can leave out the cow if you don't feel like you can pronounce it. Fine. I'm a principal right now, and I'm going to talk a little bit today about some of the fundamental assumptions we make when we do SAD modeling, and how we can figure out what assumptions are right by looking at how well the optical couples to the infrared. So I want to start with saying that on a kind of a positive note, that of course SAD fitting codes today are more sophisticated than they've ever been. They're super multi-wavelengths. They go from the X-ray to the radio. They nicely Bayesian. They estimate more things than ever. But one of the things that we've already seen a lot this week is that, because they're mainly fitted to all our old data, so SDSS and Hubble data in the optical and the UV at low redshift, they tend to have issues at doing other things. The main thing we've seen this week has, of course, been that SAD fitting codes tend to have trouble at high redshift. But I want to talk about the other nice thing you can do when you get a bunch of new nice infrared telescopes, which is, of course, just look at the infrared, but locally. These considerations of, we're going to have a lot of new infrared data coming up, spawned a question during one of my thesis committee meetings, which was, how much can I tell about the infrared emission of a galaxy if I only have information from the optical? So this is a very good question, and it quickly divided my thesis committee into two groups. And since my thesis committee consists of very smart people who know much more about astrophysics and than I ever will, and they couldn't agree on this, I figured that it would be a good idea to try to look at who was right. And since this is the 75th talk of a full week of just talks, I am going to take a page out of Samara's book and request some audience participation. Because the interesting thing with the answer to this question here is what kind of assumption it is you're implicitly making when you give your answer to whether or not this can be done, or this cannot be done. So I want everybody to take a second and think about your answer to this question here. Given an optical spectrum, something SDSS-like, is it possible to predict the mid-IR photometry for that galaxy to produce chi-square of about 1? Most people have either the absolutely not reaction, or they think it's so obvious that you can't do it that they say, of course. Everybody thinks this project is ridiculous because it's obvious what the answer is, but I want you to just take 5 seconds and think about what do you think the answer to this question is. All right, so now I hope that everybody has it. So before we go on, let's think a little bit about what kind of assumptions are driving each answer. So if you're on team absolutely not, the thing that you're implicitly assuming is some kind of separability between components. Different components of a galaxy dominate emission at different wavelengths, and so if these aren't that tightly coupled, then you really can't say anything about what's going on in the IR or what's going on in the optical, because it's different components that are separable that are dominating the emission. If you said, of course you can do this, then you are a good student of the Sandy Faber school of coupled variables, and you're assuming that the different components of a galaxy are very tightly coupled. A galaxy isn't something that you can split up into separate components. Everything is connected. That's the assumption you're making, except that of course you can do this separation fast. Of course, we have to figure out who is right, and the way we're going to do this is by using some data, because as Robert Lupton would say, data always beat assumptions. So we're going to test this with an empirical model. The empirical model we're going to be making is based on 500,000 SDSS spectra mapped to photometry from WISE. For those who don't remember, WISE is photometry at 3.4, 4.6, 12, and 22 microns, so covering kind of what we usually consider like the near-infrared, so mainly dominated by all stellar populations and AGB stars, out to where you start being dominated by PAH emission and dust emission. And then we're going to construct this empirical mapping between the two. And the method doesn't really matter. I know I got placed into the machine learning section, and I am going to use machine learning, but it doesn't really matter exactly how you do this. You can use a simple neural network, you can use a spline, you can use kind of an n-dimensional linear fit. It really doesn't matter as long as you have some way of connecting the optical to the WISE photometry. So let's find out who was right. Let's see if we can make this well. So down to chi-square of about 1. And we absolutely can. What you're seeing here in the blue is our predictions minus the truth divided by the uncertainty in each band. And just for reference, I've also drawn a unit Gaussian in orange here. So the orange line is what our predictions would follow if they were completely perfect and the errors were also perfect. So the little bit of excess here, we're getting really close to this orange line. And whether or not the little bit that's left over is because the errors aren't perfect or because we actually cannot do the prediction task is unclear. But in short, we're getting pretty close to 1. So you absolutely can do this. And so now we want to think a little bit about why did people say that you couldn't do this? Well, you go back to this assumption of separability. So that assumption was obviously wrong. But every single SED fitting model in the world makes this assumption when it comes to fitting parameters. And lo and behold, if you try to get an SED model to try to do this task where we fit the parameters based on the optical spectrum and then ask, okay, so what is the SED in the infrared? They are terrible at it. Here's an example trying to use 2 of the codes that you've already seen being used in this week, Prospector and Segal, for the 4 different Y-stands here. And here we go away from reduced chi-squares close to 1, and we go to reduced chi-squares of tens, hundreds, thousands, or even tens of thousands. So truly, truly horrible predictions. Of course, you could try to defend this assumption of separability in many ways. One of the aspects that people usually will claim some kind of separability in is the separability between AGN and galaxies. That, you can kind of try to argue this because, after all, a black hole is pretty small compared to the rest of the galaxy. Most of them have some kind of dust torus around, and so there should be some kind of separability in wavelengths anyway. Like they mostly emit in the infrared. So can you really tell what's going on with the AGN from just having the optical? But this kind of separability often leads you to having these very, very bad predictions. Where, for example, here you see a spectrum that really doesn't show much of the sign of any AGN activity, but yet Prospector here predicts this kind of very characteristic AGN torus dust bump. But it's nonsense. It really, really is nonsense. And we think that this is because these kind of codes assume separability between AGN and galaxy. And we think that this is wrong. Of course, when you're at Princeton, you have to, if you have a theory about how AGNs work, you have to go and ask 2 of the people who know most about it in the world, Jenny Green and Andy Goulding. You're very lucky to have at Princeton. And they'll say, okay, it's cool that you can get the photometry right and all that, but in order for us to believe this story, you have to show that you can derive something physical, something that we think that you cannot get right without having access to the infrared usually. You should show us that you can predict the bolometric luminosity of the AGN only from the optical. If you can get that right to about 0.3 dex, then we will be amazed. And so in order to get a good AGN sample, I went and cross-matched all the SDSS spectra with XMM Newton, so we assured that they have good X-ray detections. We took everything that's within 10 arc seconds of the SDSS pointing, and said, okay, if there's a point source within 10 arc seconds of an SDSS pointing, we think that we're pretty sure that's an AGN. And then we fitted for the bolometric luminosity using all the infrared photometry that we could find. That usually means we got JH K-band and Ys for that galaxy. And we fitted for the bolometric luminosity of the AGN, and then we went back and we tried to say, can we again make an empirical model based on the optical observations that could have predicted this? This is the result. And the main thing I want you to just see is this number here, the scatter, 0.32 dex. And so we don't quite beat Andy's goal for us, which is 0.3 dex, but we're very, very close, which earned us a coveted. That's quite impressive from Andy. Of course, you might be sitting here thinking that this is just a philosophical discussion. Like, why do I care if you put this in your SED models? It doesn't really matter. I wasn't really trying to constrain the bolometric luminosity of the AGN, just going from the optical. But you can show that there are huge parameter degeneracies that really impact the inference of some of the things you might care about if you have a spectrum, such as your star formation rate. What I show here is the error you're making in the models are making in estimating the star formation rate, in estimating the AGN fraction versus the star formation rate. You can see that those 2 things are heavily degenerate. Usually, when you get the AGN fraction wrong, you will heavily bias your star formation rate on intermediate timescales, which is this SFR2, up to about, and it's typically about a dex. Like it's a lot. It's not just like a little bit of bias; it's a lot. We can also do other things that people usually think that you need mid-IR information for. You can predict stuff like the QPH fraction. You can show that that has to be constrainable from the optical to at least 10% accuracy, which is really nice. I unfortunately don't really have a lot of time to explain exactly how we do importance mapping, so assigning importance to two different parts of the spectrum. But we use a technique that we developed in Princeton last year called multi-scale occlusion to kind of show what part of the spectrum was most important. And when we split this up by galaxy type, so star forming versus quiescent, and for each separate band, we get some maps that actually are very, very nicely interpretable. The best one, I'm just going to show quickly here, is for the W3 band. So this is for the for kind of the quintessential like PAH band for star forming galaxies, where we try to use this multi-scale occlusion to see what was most important in order for us to get this right. And of course, some of our old friends kind of pop out immediately. Some of the things that if you had sat down and thought about what would I use to do this prediction task, you would have guessed some of these things, like the H alpha, like the O3 lines, O2 lines, and some of the sulfur lines. We already heard Sandy talk about many of these lines, and they are really, really important. But you can see that this is rough. This is pretty flat. There's not that many peaks here, so it's not that many things you need to get right in order for this to be well. Unfortunately, getting those lines right is something that SED modeling codes are really, really bad at, and that's why they really can't do this task. So, to conclude on this, the optical and the IR are very, very tightly coupled. It's really, really important. Those two things are very tightly coupled, and the reason for why that's very important is because that it tells you that the physical components of the galaxy are very, very tightly coupled as well. This is really important because there is not a single SED fitting code in the world that does not break this assumption, and that leads to imprecision and biases in the inferred parameters that you get from SED fitting codes. And of course, hopefully, this is all very bleak, but you can, again, in a data-driven way, like I just showed, point to what it is that you needed to improve on in order to be able to get this right. And then, because I'm not very much a summary slides, I want to leave you with a quote from Kragh Jespersen that I think sums this up very nicely. In galaxies, everything is connected with everything. It's connected with everything. So, thank you.
Questions?
Thanks for a great talk. Colin Burke from Yale.
Yeah.
So do you have any sense of what's missing in these SED fitting codes? I mean, they're more flexible than they are physical, right?
Yeah.
So they can fit anything, but what's missing from them from a physics point of view that could help with these predictions? Thanks.
So the first thing to begin with is just ionization issues, like kind of stuff like getting, like, again, H alpha and O3 right. There are many, many papers that show that there is not not many papers. There are some papers that show that there is not a single SED fitting code on the market that gets those right. You can also go and dig into things that are a little bit more subtle, like the very detailed metallicities. For example, you can dig into something like the FE lines at around 5300 angstrom, which when we do this analysis, get to pick out as being really important for getting the flux in W3 right. Because as Caleb told us about a couple of days ago, actually pH creation is very tightly coupled with metallicity. So in order to be able to predict kind of what is going on with the pHs, you need to have some kind of metallicity in. And I know that models are often up to being flexible instead of being physical, but you cannot make pHs without having any metals in your galaxies. You need to have some kind of exclusion zone where you say, if there are no metals in your galaxies, you also can't have that many pHs. And they completely miss this.
All right. Here.
Hey.
Yeah, thanks for a nice talk. Hao-Wen Zhang from Arizona here.
Yep.
I probably have a question that I also don't know how to answer, which is, so I think your empirical model, if not more, is plagued by the fact that we do not have very large samples for objects in the extreme conditions or like that appears in the extreme parts of our parameter space, similar to, say, SED fitting. So what kind of solutions do you see that we will have in the future in addition to just getting more and more of them to make your empirical estimates more robust?
So it's a very good question because of course empirical models always suffer from like the regions of the parameter space where you don't have a lot of observations, they're just poorly constrained. The thing I'll mention is that these 540,000 SDSS spectra span a lot of things. There's not anything that really goes that poorly. So I would say that most of the things that we think are extreme cases are actually the normal things like that aren't too far away from what what can happen in normal galaxies. Again, I was expecting there to be like something that would break this empirical model, like ATMs, super dusty galaxies, but it never really breaks. And I think that was actually kind of surprising to me that it never breaks. But the thing that I think that implies is that galaxies really are confined to kind of very narrow tracks. Again, just like Sandy was telling us about earlier, that like most things have to lie on tracks, and that there aren't anything that really deviates like completely outside of the normal, even if they look extreme and abnormal to our eyes.
Right.
Would you like to comment whether this, call it a galaxy central limit theorem, works because it's galaxies, or do you think that subparts of galaxies are also subject to these relationships in as good quality as what you found? It could go both ways. My mind, I hope you give me some insight.
I haven't done this myself, but I would say that there's been recent work by Dalia Baron, who tried to do a similar thing for the Planck survey, and actually found again that you can connect the optical to the IR pretty strongly on sub-PASIC levels as well. So I think that I think that there are things on sub-galaxy scales where these things also hold. That there are only that you can't really spray that. Like you can determine what's going on in the IR. There is a strong coupling of different components even on sub-galaxy scales. But of course, it's easier to do when you have a lot of them.
As Joe set up, we can have a very quick question.
Thanks for the nice talk. I was wondering, this separability issue might also depend on the data quality, let's say, right? At some point, if you are, imagine you want to predict not only some basic wise photometry, but you want to have a full shape of the SCD or the spectra, very, very high resolution in the infrared. Then this must break down at some point, right?
It should break down at some point. There is some level of detail that you get at some point that you can't get into the detail in some cases. But of course, that's the case. You want to get detail in that. So that's the question. Exactly where that happens, I don't know. You don't have a lot of nice details like IR spectra, so kind of making a model like this. A little harder there. But I'm very, very happy to try in case you have to use maybe one.
Let's thank Christian again.